There are different grades of GPS, and depending on what your application is really going to drive which grade you select. There's recreational grade, mapping grade, and survey grade. And generally, recreational grade is the least expensive, mapping grade is medium, and survey grade is the most expensive. And what really drives the cost of the GPS is the accuracy of the position. And so if your application really doesn't require that accurate of a position, for example, hiking, fishing, running, then you might utilize recreational grade GPS, which will give you a horizontal accuracy of 3 to 5 meters and is good for finding your general location and using for navigation. Mapping grade GPS typically has a little higher horizontal accuracy from 1 to 5 meters. It's great for not just finding your location, but also for collecting data. And we typically use mapping grade when our application is not just about collecting a fairly accurate position, but we also need to collect attributes associated with that position in the field. Now, survey grade GPS is all about accuracy. It typically is accurate to sub-meter or maybe even sub-decimeter. And so it's great for finding a specific location, and you can also often use it for collecting attributes as well. Professionals typically use survey grade GPS for conducting field surveys. Now, I've got one more advanced geodatabase object that I want to talk about this semester, but before we do, let's go back and review what a geodatabase is, which is basically a container for storing spatial and attribute data and their relationships. And if you remember, there were three basic data types that we store in a geodatabase. That's tabular data, vector feature classes, and continuous raster data sets. Now, a raster data set is a single geodatabase object in which cells are arranged in rows and columns with associated values. And in the example that you see below, on the left-hand side, you can see a hillshade of the United States, which is the illumination of the landscape in the United States. And if I zoom all the way in, it pixelates out into individual cells that are assigned a value. And the more illuminated the landscape, the brighter, the higher the value, and the less illuminated or the darker the landscape, the lower the value. So a raster data set is pretty easy to work with and pretty straightforward if it's small, but sometimes we'll download, for example, all the imagery for Texas, and suddenly it can become really unwieldy. So we need an advanced geodatabase object to help us with raster management. And that's a mosaic data set, which is a container for managing, displaying, serving, and sharing raster data. So if we have a large set of image data, we can use mosaic data sets to display the tiled images as a single layer. So we don't have to load 100 images into our GIS software. We can load one mosaic data set that then loads the 100 images tiled side by side. We can also run raster geoprocesses on tiled images as a single layer. So instead of having to run, for example, slope on a whole bunch of different DEMs that I have individually, I can create a mosaic data set, load the 100 DEMs I have, for example, into that mosaic data set and run one slope process on the entire data set. It also allows you to tweak properties like compression. So you create mosaic data sets as an empty container, and then you add your rasters. So if you look in the image there on catalog, I'm right-clicking on the geodatabase, selecting New and Mosaic Data Set, and that opens up the Create Mosaic Dataset geoprocessing tool. That's creating a mosaic data set that is an empty container. And then once it's created, and you can see in catalog there, I've created an orthoimagery mosaic data set. I can right-click on that empty mosaic data set and select Add Rasters. That will open the Add Rasters to Mosaic data set, which then allows me to pick all the different images or DEMs or whatever type of raster data set that I'm trying to tile, and allows me to load that into my mosaic data set. At this point, you should be able to differentiate between triangulation and trilateration. Triangulation is where you calculate your position using angles, and trilateration is where you calculate your position using distances. You should be able to describe the space, control, and user segments of GPS. Space are the satellites themselves. Control are the facilities on the ground that help manage the satellites, and the user is actually you holding the receiver that you need to calculate your position. You should be able to list the types of GPS error that degrade your positional accuracy, and then explain how we use differential GPS to mitigate that error. You should be able to differentiate between image data, which is a single raster data set, and a mosaic data set, which is a collection of raster data sets stored and managed as a single object in a geodatabase. And last, in the demonstration and project, you'll be able to configure GIS data for collecting GPS field data.